Let me start. Hi, everyone. My name is Ang, and I'm from the USA. Today, I will give a talk about our paper, a FastMap-based algorithm for block modeling. First, I will give an overall explanation about our program and how we propose the method to solve it. And then I will, and then I will introduce some background knowledge for the block modeling and the FastMap, which we are used to solve the block modeling problem. And then I will introduce how we adapt a FastMap to solve the block modeling problem. And after that, I will. I noticed that. I think I'm muted. Okay. So, and then I will talk about the experimental results and the visualization. And finally, I will talk about the conclusions. So what's block modeling? So block modeling is a graph version of the clustering program. It requires to cluster vertices of a given graph G. And the vertices can represent individuals, agents, objects, and etc. And the edges will represent the relationships among those vertices. In practice, there are many algorithms that will solve the block modeling problem on the graph directly. However, working directly on the graph will be computationally expensive and less effective for the large complex graphs. So how can we avoid this? In our method, we propose to first embed the graph into the Euclidean space so that we can solve the problem in the Euclidean space, and then we will avoid to working on the graph directly. So how can we do this? In our method, we propose to use FastMap to do this. We will first use FastMap to do the embedding. And in our adapted version of FastMap, we can generate the embedding in near linear time while preserving all the desired properties of the original graph. And actually, once we have the embedding, it leverages any techniques for the clustering in the Euclidean space. And in our method, we simply use the GMM, the Gaussian mixture clustering method. Now, let me give you more background knowledge about the block modeling problem. I will start with the community detection. Community detection is a simple version of the block modeling. In community detection and the block modeling problem, it requires to mapping each vertex of a graph into a cluster. And each cluster can also be called as a community or a block. And within each cluster, the vertices will share important similarities in the underlying graphs. In the community detection, it usually assumes that there are typically more intra-community connections than the inter-community connections. And the community detection has many applications, such as social networks, protein-protein interactions, recommendation systems. However, the community detection doesn't always work well in some general cases because it's not always true that the intra-community connections are more than the inter-community connections. And in this case, we will use block modeling. Block modeling is a generalized version of the community detection problem. It will use more general criteria where the community detection fails, and within each block, the block members will behave like each other. For example, as this figure showed, the block modeling can be used to identify the groups in a core-free graph. In a core-free graph, there are two sets of vertices. The core set of vertices, which are tightly connected to each other, and the periphery set of vertices, which are loosely connected to each other, but well connected to the core. Core-free graphs are common places in many real-world domains, such as airport connections and financial networks. And in block modeling, there is a commonly used objective function. It is to minimize the differences between A minus C multiply M multiply C transport. Here, A is given, which is the adjacency matrix, and C and M are what we want to design so that we will minimize this term. C is the membership matrix, which will indicate which vertex belongs to which group. And M is the image matrix, which will indicate how tightly members of two groups are connected. So For the block modeling problem, how can we avoid to solve it on the graph directly? We can embed them into the Euclidean space first. And in our method, we propose to use FastMap to do this. So FastMap can, in our adapted version, it can be used to embed a graph in near linear time. And it will at the same time at the same time, the pairwise the Euclidean distances will approximate a desired graph-based distance function between the corresponding vertices. And in the original FastMap, it is used in the data mining domain, which is used to embed a collection of unabstract objects in the Euclidean space in linear time. And two things I need to highlight here. One, the pairwise Euclidean distances will approximate a desired distance function between them. Second, O(n) square pairwise distances will be preserved in linear time. And by embedding the graphs or the objects into the Euclidean space, it will enable geometric interpretations, algebraic manipulations, and downstream machine learning algorithms. So let me first start with the original FastMap in the data mining. And then I will explain how we adapted to FastMap to solve the block modeling on graphs. So why FastMap is important in the data mining? Because it allows us to solve problem on abstract objects with a method that can only be applied in the Euclidean space. For example, clustering is a very common problem, and there are many well-developed methods for clustering in the Euclidean space, such as the Gaussian feature model clustering and the k-means clustering. However, this method cannot be applied to the abstract objects directly, such as files and documents, images and videos, and data strings. However, we can use FastMap to embed them into the Euclidean space first. And once we have the embedding, we can apply the clustering algorithms such as the k-means and the JMM clustering. And one key component of FastMap is the distance or the similarity function. So the distance function will return a well-defined and a computable distance, DOI-OG, between any two objects, OI and OG. For example, the constant similarity between two documents, and the missing constant distance between two images, and the added distance between two data streams. So the FastMap will embed all the objects in a k-dimensional Euclidean space, where k is user specified, and the Euclidean distances will approximate the given pairwise distances. So what efficiency requirements we want here? We want the running time to be O(n), while we will also want to have to preserve the O(n) square pairwise distances at the same time. And the FastMap can achieve this. So the details can be found in the paper. So I will simply make a summary of the benefits of the FastMap. So the FastMap embeds n objects in a k-dimensional Euclidean space. The running time is OKN, where k is user specified, representing a trade-off between memory and accuracy. And FastMap has plenty of applications in data mining. However, FastMap assumes that for any pair of objects OI and OG, the distance DOI-OG can be computed in the time independent of OI. So with this assumption, how can we apply FastMap to embed a graph? Because in a graph, we can simply treat a vertex as an object, but usually the distances between vertices are usually calculated by a graph-based distance function. And the graph-based distance functions are usually dependent on the size of the graph, which is not independent of n. So how can we do this? How can we embed the graph into the Euclidean space of in near linear time? Let me give you an example of the shortest path distances. So where the definition of the shortest path distances is very simple. The cost of computing the shortest path distances between two vertices in an undirected graph will depend on the size of the graph. So how can we achieve the embedding in near linear time? So let me first give you a high-level picture of how FastMap do the embedding. So the FastMap will generate the k-dimensional Euclidean embedding in k iterations iteratively, and in each iteration, it will first identify the first pair of two vertices OA and OB. This can still be achieved heuristically in near-linear time of a graph. And after that, it requires to compute the DOA-OI and the DOI-OB for all OI and fixed OA and OB. And if we simply calculate the DOA-OI once, then it will not near linear time because it will depend on the size of the graph. However, we simply calculate the shortest path trees rooted and OA and OB, because by doing so, we can have all the DOA-OI and DOI-OB at the same time, and on average, the time to compute each distance is near constant, because the time complexity of the shortest path tree function is OE plus n log n. Here, n is the number of the vertices of the graph. And when the graph is sparse, this time complexity can be approximated as O1 after ignoring the logarithmic factor. And overall, to generate the k-dimensional Euclidean embedding, the time complexity is still near OKN. So here is the summary of the benefits for the FastMap for graphs. So FastMap can embed a given weighted graph in the Euclidean space in near linear time, where preserving all pairs of the desired graph-based distance, and it doesn't depend on techniques like machine learning. And thus, many graph problems can be solved by the geometric methods. So after the introduction of those background knowledge, and I guess you can already guess how our FastMap method works for the block modeling problem. So in our paper, we propose the FMBM, a FastMap-based algorithm for block modeling. It has two phases. In the first phase, it adapts FastMap to embed a given graph in the Euclidean space in near linear time, where preserving a desired distance, the graph-based distance among all the vertices. And in doing so, it helps to avoid solving block modeling problems on the graphs directly, which will be computationally expensive and less effective when the graph is large. And in the second phase, once we have the embedding, we simply perform the GMM clustering. Actually, because we have the embedding, it leverages any techniques for the clustering in the Euclidean space. And one key thing here is that which distance function we want to use here, because the distance function is very important to the FastMap. On the first thought, we simply will try the shortest path distance, but the shortest path distance doesn't always work well. For example, like in this bipartite graph, the vertices are actually closer to each other for the vertices that are from different partitions, and the vertices in the same partition are actually farther to each other. And if we use the shortest path distance function, then the vertices in the same partition should have a higher similarity. Thus, the shortest path distance is not a good measure. Actually, the embedding here shows that if we use the FastMap with the shortest path distance function to embed this bipartite graph, then we will get the embedding like this. We can see that there are, many vertices from different partitions actually overlapped with each other. So what distance function we want? Based on the cases like the bipartite graph, we design the three guidelines for the distance function. So for any two vertices, we want that if there is a smaller shortest path distance between them, then we also want the actual distance smaller. And the second, if there are more existing passes between the two vertices, then we also want the desired distance smaller. And third, we want the complement graph yield the same distance function. And this is for the unweighted graph, because in an unweighted graph, the same relationship between vertices should be able to encode it either as non-edges or edges. And actually, with these guidelines, we designed a desired distance function, And with that list function, our FastMap method can actually work very well with more general cases. For example, for this bipartite graph with the desired list function, we can get the embedding like this. The two partitions are separated well in the Euclidean space. And for this core-free graphs, the Euclidean embedding also shows well. The core part and the free part also separate well in the Euclidean space. And here is the high level idea of the distance function we designed to satisfy the three guidelines I mentioned just now. So we will generate the subgraphs of the original graph G by dropping edges with the probability P, and also I generate the complement graph of the G, and then I do the same as the procedure I did in the first step. And finally, I will let the distance be the sum of the shortest path distances of all the subgraphs generated in the first two steps. And overall, in linear time, we can still convert the problem to a regular GMI clustering problem in the Euclidean space. Now let me show you some experimental results. In our experiments, we use some benchmark test cases and synthetic test cases, and we use three evaluation metrics: the value of the objective function, the normalized mutual information gain. This is with respect to the ground truth. So this NML value is a measure of how similar of our solution is to the ground truth. It's between 0 and 1. A higher value indicates a better solution, and the running time in seconds. And we compare the following solvers. Graph 2. Graph 2 uses augmentative multi-level Markov chain or multi-column method, and DNMF, which uses alt-deep encoder, and the CPAIOR, which uses constraint programming with large neighborhood search. And here shows some results from our experimental results. The carried instances is from the benchmark instances. And the second one is the complement graph of the first one. We generate the complement graph of the benchmark test cases is to test the robustness of the solver against encoding the same relationship, either as encoded as non-edges of all edges. And in our experimental results, only our method and the CPRS pass this test. And the last two instances are from the synthetic datasets. And I didn't list the running time here because the graph 2 will always have the smallest running time. But when the graph became very large, the FMBM will have smaller running time than the other remaining solvers. So, and overall, from this result, we can make the conclusion that the FMBM outperforms other solvers on the benchmark and the synthetic test cases in the value of objective function, the normalized mutual information value, and the running time. Another thing I need to highlight is that FMBM also enables a particular serialization of blocks in graphs, which other methods cannot provide. For example, in the graph shown here, it has 1,600 vertices and around 4,000 edges. Because it has a lot of vertices and edges, so many of the vertices and edges are overlapped with each other. So with a standard graph visualization procedure, we cannot see it very clearly. However, if we embed the graph into the Euclidean space, even in a three-dimensional Euclidean space with FMBM, we can see it much clearly because now we have a three-dimensional perspective. And you can see here, the shapes, the boundary, and the trend of each block are much more clear now. Now let me give you the conclusions. So in our method, in our paper, we propose the FMBM to avoid solving block modeling problem on graphs directly, because this will be computationally expensive and less effective when the graph is large and complex. And the FMBM has two phases. In the first phase, it adapts FastMap to embed the graph into the Euclidean space in near time, while preserving the desired distances among all the vertices. And in the second phase, it simply performs GMM clustering. Actually, the embedding leverages any techniques for clustering in the Euclidean space. And based on our experimental results, FMBM also performs many other state-of-the-art methods, both in the solution qualities and the efficiency. And also, FMBM enables a prospective visualization of blocks. And in the future, we will generalize the FMBM to work on direct graphs and multi-view graphs, and then apply it to various real-world domains. Okay, that's all. Thank you.
Questions? Yeah. In what dimension do you embed the graph? What is K? The factor K?
Yeah, so basically, when we do the embedding, the K is user specified, and usually, and in our experiments, we simply set K to 4, and simply set K to 4, we can actually get very good results.
But do you see an impact on that factor?
Yes, so generally speaking, if we have a higher K, then we have a trend to have better results. However, if K is too high, which means that, if K is high enough, then the dimensionality will have the enough capacity to explain the original information of the graph. Then after that point, a higher dimensionality will cause no actually better results. Yeah, thank you.
Yeah. Can you easily deal with directed block modeling with directed graphs? How do you do that?
Yeah, so I think the key thing here is that how we design the distance function on a multi-view graph. So if we can come up a well-designed distance function on a multi-view graph that will return a desired distance in a time that is constant or near constant on average, then I think we will be able to do it on the multi-view graphs.
Is that too much?
Oh, yeah, the same way. So directed, then the distance will be not symmetric. So we want to deal with how can we represent this distance, or how do we use the distance in an unsymmetric way. Yeah.
And the stochastic block modeling can also deal with the volatility. The one with weights, so it's not a 0-1 edge. In the original graph, it's a weight.
So you mean on weighted graph?
Yes.
Yeah, so on weighted graph, we may want to change some designs, like I think in the weighted graph, the first two guidelines are still apply, but the third one may not be applied, because on a weighted graph, the relationship cannot be simply encoded as edges or non-edges. So maybe for the weighted graph, we may need to do some guideline changes, and then we can adapt it.
So have you tried any considerabilities like end-to-end approaches? So in a sense, what you're doing is you're doing like a projection first and then doing clustering, right?
Right.
So there's been a lot of developments on end-to-end approaches for this kind of settings, including Brian Wilder in the masterclass talked about the cluster net, where essentially it's learning like the neural net, which is projecting in a space and then running a differentiable version of k-means. But there's obviously many others. So I didn't see any comparisons to end-to-end.
Right, yeah. So yeah, I think that's a good point. So in this paper, we only focus on that the comparison with the method that will dealing with the graph directly. Yeah, I think you make a good point. We should include the comparison with the other methods that will do the end-to-end like this. Yeah.
The machine learning community is the one mostly working on this problem, right. So they'll have many more sophisticated.
But the scalability is an issue. No? They can scale to millions of nodes.
Can we scale to millions of nodes? The CPAIOR? But in the data mining community, they do solve clustering problems. I think some of the methods.
Yeah.
So let's take the classical continuity projection. So then you use modularity as the objective. Then that's empty complete. Right. So I don't understand how all this embedding helps to solve the problem.
Yeah. So basically, in this embedding,
and also does that affect experiment? the experiment kind of thing, or I didn't understand the experiment.
So you mean how can we avoid this NP hard property of the block modeling problem? So I mean, so
How do you solve the NP hard?
no, we don't solve the NP hard problem. That will be a huge impact. So basically, here we use the FastMap to do an approximation. So basically, in here in the FastMap, we will do a heuristic way. So in this heuristic way, while we do the embedding, we do the embedding in near linear time. We can still preserve the O square pairwise distances, and then we take this advantage to improve the efficiency.
So understand, and this is some kind of approximate method, but then can you say something about the qualitative result?
So
Not by experiment.
yes. So what's your question about the results?
So this is some kind of approximation method now, right?
Right.
Then do you know something about, what is this approximation?
You mean how good is this approximation?
Right.
Yeah, I mean,
Something.
yeah. So that's a very fair question. So I mean, I didn't show it here directly, but I mean, based on our experiment results, like not for this distance function, like for simple version, like for the shortest path list function, if we use the all pairs shortest path list function to generate the actual distances, and then we use the FastMap to the embedding, and then we get the distance matrix of those embedding in the Euclidean space, we found that actually the distortion is very minimal.
Okay, I think we should move ahead for next talk. So thank you again.
Yes, thank you.